the continuation of horizontal range, we have a special case, which is that when does this range of the projectile will be maximum. Okay, so in order to find the maximum range of projectile, it is said that the range of projectile will be maximum if sine 2 theta is maximum. Okay, so sine 2 theta is maximum. So as you know that sine, when is that sine function is maximum? When it is 90 degree, correct? So hence you can write here theta is 2 theta is equal to 90 degree. Okay, that is nothing but equal to theta will be nothing but equal to 45 degree. So when the angle made with the horizontal, when the object is thrown, okay, in the air, which makes an angle of 45 degree with respect to the horizontal surface, so it covers a maximum distance. Okay, it covers a maximum distance. So this is regarding the maximum range of the projectile. Okay, so hence when theta is equal to 45 degree, so r value comes out to be maximum, that is nothing but equal to u square by g. Okay, that is u square by g. Okay, so it is said that thus the projectile has the maximum range if it is projected at an angle of 45 degree with the horizontal. Okay, so that is what I said, when the projectile is projected at an angle of 45 degree. Okay, so it covers the maximum distance. Okay, so this is regarding the there is a maximum range of projectile. Okay, so second case is not important. Okay, we will just leave out that. So next you can see the figure. Okay, so which are nothing but the examples of this projectile. Okay, that is the path, the trajectory of the projectile is nothing but it is a parabola, right? So that is what we are seeing in the figures here. So these are nothing but the projectile related figures. So the next topic is nothing but it is regarding the uniform circular motion. Okay, so coming to this uniform circular motion, I think you have been come across this uniform circular motion, centripetal acceleration and all in your lower classes itself, I think. Anyhow, we will just go through. So let us go through what do you mean by this uniform circular motion. So it is said that when a point object is moving on a circular path with a constant speed, then the motion of the object is said to be a uniform circular motion. Okay, when the point object is moving in a circular path with constant speed. Okay, so that type of motion of an object is said as uniform circular motion. So the next is, the word uniform refers to the constant speed. It means that in uniform circular motion, the object covers equal distances along the circumference in equal intervals of time. That is, the speed is constant. Although the magnitude of velocity, that is speed, remains constant, the direction of velocity is changing continuously. Therefore, the object is undergoing acceleration. This is called centripetal acceleration, and it is directed radially towards the center of the circle as shown in the figure 12a. So as you know that when you keep on revolving a object with a constant speed, as you know that it covers equal distance in an equal interval of time, right? But the speed remains the same, that is the velocity remains the same magnitude wise, but the direction differs. Okay, so at each point the velocity direction keeps on changing, so hence this give rise to the acceleration. Okay, and this type of acceleration is called as the centripetal acceleration, and it is always, I mean, it is directed radially towards the center of the circle, as you can see in the figure 12a. Okay, so the centripetal meaning is nothing but it is said that it is center seeking. Okay, so just go through the figure 12a and understand the concept. So then we will move to that expression for centripetal acceleration. As of now, just go through the explanation part and the figure 12a. Okay, so now we shall move to that expression for centripetal acceleration. Okay, so this derivation is for 5 marks. Okay, they usually ask this derivation, derive an expression for centripetal acceleration. Okay, and it is a 5 mark question. Okay, so if you just go through the question paper, you will come to know. So let us start with this expression for centripetal acceleration. There is nothing but, consider an object moving with a constant speed v around a circle of radius r as shown in the figure 13b. Okay, you can see in the figure there. Okay, an object is moving with a constant speed with the speed v around a circle of radius r. At point a, its velocity is represented by vector a is in the direction of the tangent to the path at point a. After a short time delta t, the object is at point b and its velocity is vector vb is in the direction of the tangent to the path at point b. During the time interval delta t, the object moves from A to B covering a small distance delta L along the arc which subtends an angle, small angle delta theta at the center O. Okay, at the center O. Note that magnitudes of velocities at point A and point B are the same since the speed is constant. That is vector A is equal to vector B, that is nothing but equal to vector V. Sorry, V. Okay. However, direction of velocity differs at point A and B, hence the object has acceleration. Okay, so see you. What we have done is we have just consider an object moving with a constant speed with a constant speed v around a circle of radius r. Okay, around a circle of radius r as shown in the figure. At point A, you can see there. Okay, consider any point. So in the figure, I'm going to consider at point A. Okay, as you know that in order to calculate the direction, okay, in order to calculate the direction of an object at that particular point, okay, so what we are going to do is we are going to draw a tangent there. Okay, so tangent gives the direction at that point. Okay, next consider point B after some time interval delta t. Okay, consider another point, that is B. So again there, in order to calculate the and in order to find the direction, so what we are going to do is again we are going to draw a tangent. Okay, you can see that the tangent which has been drawn there, vector A and vector B. Okay, vector va and vector vb. So what happens here is, since you know that the object which is moving from point A to point B, so making an angle of delta theta in a time interval delta t. Okay, so what we are going to do here is, we will say, we will consider that it covers a small distance delta L. Okay, so here it is like, what we are going to do is consider a circle. Okay, consider a circle. So what we are going to do is, we are going to consider only a small part of this. Okay, when you consider a small part, so when you see that small part itself, what happens, it will be almost like a straight line. Okay, it will be almost like a straight. Okay, only when you consider a greater part, you'll when you consider the greater part, you will come to know it is an arc. Okay, but when you consider a very small part, okay, we can consider that as a straight line. Okay, so that is what we have considered here. You can see from point A to point B. Okay, we have drawn a straight line there. So straight line is nothing but which covers a small distance, that is delta L. Okay, so this is regarding the explanation of the figure. So next, let us say that, since you know that magnitude wise, okay, direction of velocity changes at point A and point B. Okay, you can see in the figure itself, but the magnitude remains the same at point A and point B. Okay, so hence we are going to write that as vector va is equal to magnitude of vector va is equal to magnitude of vector vb, that is simply considered as v. Okay, so next is the change in velocity vector delta v vector is given by delta v vector is equal to vector vb minus vector va. Okay, obviously, so delta v can be considered as vector vb minus vector va. So here what we have done is, we have considered the same thing. Okay, we have drawn another figure here. Okay, where you can see in the figure, this is the vector va. Okay, and this is the vector vb. Okay, and we have just made an angle delta theta between vector a and vector vb. Okay, so next what we have done is, so that difference, that is delta v vector. Okay, it is nothing but expressed as vector vb minus vector va. Okay, so that is the change in velocity is represented by delta vector v, that is nothing but equal to vector vb minus vector va. Okay, so just what we have done is, with reference to this figure, we had drawn another figure which is almost the same. Okay, only the thing is, here we have taken delta L, but here we have taken as delta vector v. Okay, so hence the value of delta vector v comes out to be as vector vb minus vector va. Okay, so next, it is regarding magnitude of centripetal acceleration. Okay, magnitude of centripetal acceleration. As you know that the vectors vector vb, vector va, and delta vector v in the figure form a triangle that is geometrically similar to the triangle abo. Okay, so if you compare these two triangles, okay, it is almost similar. Okay, so this triangle is almost similar to this triangle. Okay, so comparing this to, what we are going to do is, we will write delta v by v is equal to delta L by R. Okay, see in the figure here, delta v is nothing but, this is the value of delta v here. Okay, so this is delta v, and we have taken any one of the value here, either delta v va you can take, either delta vb you can take. Okay, so magnitude wise, what we have written, delta va and delta vb is nothing but equal to v itself. So hence what we have done is, delta v by v, delta v by v is equal to delta L by R. So compare that with this figure again here. Okay, so R is the radius here, and delta L is a small distance covered. So hence you can write delta L by R. Okay, just comparing both the figures. So next, delta, or it can be written as delta V is equal to V by R into delta L. Okay, so the value of delta V is nothing but equal to V by R into delta L. So it is said that this becomes an exact equality when delta T extends to 0 for the delta L equals the chord AB. In order to get the magnitude of centripetal acceleration A subscript C, we use the above relation for delta V and write A subscript C is equal to limit of delta T extends to 0, that is nothing but equal to delta V divided by delta T. See how we are going to define the acceleration. Acceleration is nothing but equal to delta rate of change of velocity divided by rate of change of rate of change of velocity divided by time. Correct. So that is what we have written here, but we have taken with a limit here. Okay, where limit delta T extends to 0. So that is nothing but A subscript C is equal to limit delta T extends to 0 delta V divided by delta T. That is nothing but equal to limit delta T extends to 0 into V del R divided by R delta T. Okay. So what we have done is we have just substituted the value of delta V here. So delta V value is V delta L divided by R delta T. Okay. So the next is we will take out that V by R outside. So V by R it's taken outside. So limit delta T of T extends to 0 into delta L divided by delta T. Okay. So V by R we have retained the same. This delta L by delta T is nothing but similar to that of rate of change of displacement divided by time. Okay. Delta L divided by delta T is rate of change of displacement by time. Okay, so into V we have written there. So hence A subscript C is nothing but equal to V square by R, which is called as the expression of centripetal acceleration. Okay, centripetal acceleration is also called as radial acceleration. Okay, and it is said that since V and R are constant, the magnitude of centripetal acceleration A subscript C is constant. Okay, but the direction of AC is not constant. As you know that V and R are constant here. Okay, R is a radius and V is a speed or velocity. Okay, so magnitude wise it is same, right? So hence the centripetal acceleration magnitude wise is also will be a constant, but since the direction of velocity changes, okay, so what happens, even the direction of acceleration is also changes, which does not remains the constant. Okay, so it is said that linear velocity v and vector ac are perpendicular to each other at every instant. Further, the directions of v and vector ac are changing continuously as shown in the figure. As you can see, the centripetal acceleration direction and velocity are perpendicular to each other. Okay, and this direction of centripetal acceleration is always directed towards the center. Okay, as you can go through in the figure here, you can just see in the figure here. Okay, so just go through this derivation once, then we will go to the direction of acceleration. Just go through.
ಪಾಠ ಮಾಡ್ತಿದ್ಯಾ? ಗೊತ್ತಿಲ್ಲ.
ಅದೇ ಮಾಡಿರೋದು. Yes, any doubts? Okay, students, have you understood that derivation? Any doubts regarding that expression for centripetal acceleration? Okay, students, fine. So I'll do one thing. I'll just forward these notes of this expression for centripetal acceleration. Just go through once. Okay. So read it by yourself. So in the next class, we will start with the direction of acceleration. Okay. So I want to make sure that you have understood this expression for centripetal acceleration. Okay. So once you have understood, we will go through that direction of acceleration. Okay. So please go through this derivation since it is a 5 marks question. It is a sure question in your examination. Okay. They keep asking this question. Okay. So just go through. So in the next class, we will continue with the next. Okay.